we've looked at the two different types of waves, longitudinal and transverse. We're now going to have a look at certain properties or characteristics of those waves. You can see here we've got two graphs that we're going to notate. First of all, before we do though, I just want to point out that when we're looking at graphs of motion of waves, they show the displacement of the particles from the equilibrium position. So whether it's at a longitudinal or a transverse wave, the graph will basically look the same. So these situations here that we're dealing with could either be longitudinal or they could be transverse. Before we start though, need to just notate what these axes are. So first of all, on the horizontal axis, on the first one, we're going to have time. Now these might look like different graphs, but they actually do represent the same motion of a particular wave. And so in this case, on the horizontal axis, we've got the displacement of particles, or more specifically the displacement of a single particle, and down the bottom we've got the displacement of particles as well. So as I said, the graphs that we're looking at here are dealing with the particle displacement. The difference though is that up the top we're only looking at one particle and how it moves with time. Down the bottom we're looking at how particles along the wave are changing, and so this axis here will actually be distance along the wave itself, or distance along a medium. So you can think of it as being the top graph shows one particle at various times, so each of the points in time that we might record as we move along throughout time, that shows us what the displacement of the particle is, whereas down the bottom it shows us lots of particles but at only one time, or one particular time. So if we wanted to see what would happen with all of those particles at a different point in time, we'd need another graph showing displacement versus distance. Now I mentioned before about these graphs showing not really having a distinction between transverse and longitudinal. In order to distinguish between them, what you basically need to do is identify what that means and what that means. For the case of a transverse wave, that would be up and that would be down. But in the case of a longitudinal wave, up might be, say, to the right, and down here might be to the left. So still just looking at the displacement of the particle from its equilibrium position. So as I said, these graphs could represent either transverse or longitudinal waves. Now, as we go through, I'm just going to notate what the particular properties or characteristics or quantities are that we need to be aware of, and then we'll describe them in more detail underneath the graphs. So the first thing is this quantity here, which is known as the amplitude, has a symbol capital A. And you'll notice that on both graphs they have the same amplitude because they're representing the same wave. So that displacement of the particle from its equilibrium position will be the same. The next one to have a look at up the top, you'll notice that we're sort of identifying two consecutive points on the wave that are doing the same thing. So from a trough to a trough, we could also do, peak to a peak, we could also do from a trough to a trough. We could likewise do from a zero crossing, where it's, in this case it's going down through the equilibrium position, and so we could notate that distance there as well, or that time I should say. The symbol that we give that, it's the period with a capital T. Down the bottom we have a similar quantity that we need to look at, but instead of being related to time, it's now related to distance. So we're looking for that distance there, that's lambda, which is the wavelength. So we'll jot down what each of those mean and give a bit more context to what those quantities are, but ultimately the ones we're most interested in, amplitude, period and wavelength, and there's a couple of others that tie into those as well. So first of all, amplitude. The easiest way to consider amplitude is that it is the maximum displacement from the equilibrium position, maximum displacement of a particle from its equilibrium position. Now you could, you might sort of think, well, do we deal with it going up or going down? Amplitude is generally, you sort of consider it to be the positive amount, and so usually you'd go from, say, the equilibrium position to its maximum. In some cases, it's easier to consider what the top and bottom is. So if we've got say the heights of tides, for example, it might be easier to identify that that might be, say, 12 meters, and this might be, say, 10 meters. So you know that the equilibrium position in there is going to be halfway between them, so it's got to be 11. But in that case, if we don't really care about the equilibrium position, we can take the maximum displacements, divide by 2, so the difference there being 2, so that means that the amplitude in that case would be 1 meter. So just something to keep in the back of your mind. While the displacement, the amplitude is measured from the equilibrium position, there are a few different ways that you can identify what the amplitude is. Usually amplitude will be measured in meters, given that it is a distance or a displacement, but we can't always define it that way, so it depends on the scenario. The second property that I want to look at now is the wavelength. It's probably the next easiest to make sense of. The letter that we use there is the Greek letter lambda, and wavelength, as the name suggests, it's a distance or a length over which the wave repeats itself. So that could be that we're looking from one peak to the next peak. It could be that we're looking from one trough to the next trough. It doesn't really matter what point on the wave it is that you're observing. You're just looking at the fact that or even a compression to a compression in a longitudinal wave, you're looking for that repeating pattern of the distance between those two things. The next one then that's similar but slightly different is the period. And period is not just it's not the distance now, it's the time over which the wave repeats itself. So with distance, it's literally like you'd sort of grab a ruler and measure how far it is between adjacent peaks. With period, you need to sort of grab a stopwatch, look at a particular point in space, and time from the passing of one peak to the passing of the next peak. Now, generally speaking, time is measured, the SI units for time are seconds, and so period would usually be measured in seconds. Now, there's another quantity that you can't really represent graphically, but something that's useful in order to quantify a wave, and that's frequency. Now, frequency is a little bit harder to measure. You'd usually sort of need something to do with period in order to figure it out. But you can think of frequency as how often a wave repeats itself in a given time period. So the way that I like to describe these is to there's a very clear link between period and frequency. So if you think about period, the other way to think about it is that it's the number of seconds per cycle. So how many seconds does it take for one cycle to be completed? Whereas frequency, basically just going to reverse those two. It's the number of cycles per second. So they're very clearly linked, and you can see there that it's literally just sort of finding the inverse, and that leads to the equation then for frequency compared to period, f being equal to 1 on t. Now that one is an important one, so I'm going to highlight it. It's in the data booklet, and so f is equal to 1 on t. In this case, we'd usually have time measured in seconds. And frequency then, note that we're saying that it's cycles per second. If we're talking about cycles, we're literally just counting. There's no measurement there, it's just how many, whether it's 1, 2, 3 or 4 or some fraction of that or some ridiculously large number. So frequency is measured in per second, but we usually relabel that to the units of hertz. So if you hear the frequency stated in hertz, it really just means the number of cycles per second. So this is the unit that we're going to more commonly see, but keep in the back of your mind that it basically just means the same as per second. The last quantity that we need to deal with is actually easier to start off by looking at the wave equation itself, rather than just stating what it is. So with the wave equation, if we're looking at a longitudinal or a transverse wave, a peak or a compression region travels along through the medium. So we saw that in the previous video, that as the wave is traveling, we can follow a peak or a trough or a compression or a rarefaction, and we can see that that actually travels through the medium. And if it's traveling through the medium, we can then measure how far it's traveled, and we can time how long it takes to travel that distance. So that means we can calculate the wave speed. So that's the last quantity that we need to look at, is the wave speed itself. Now, wave speed is most easily calculated by considering the distance, as I said, that the peak or the compression travels, and the time that it takes to travel that distance. Generally speaking, though, if we're dealing with waves, we're not worrying about any sort of random distance. We've got a distance that we can refer to, being the wavelength. So if we know what the wavelength is, so the distance over which a wave repeats itself, and we compare that to the time over which the wave repeats itself, we can then calculate what the wave speed is. Notice that wavelength would usually be measured in meters, and period would usually be measured in seconds, and so we end up with that the wave speed being measured in meters per second. So just a little side note there for the about the units. However, in this particular case, we are probably not usually going to use the period. It's not so much a period that would be useful, particularly when you consider, say, the frequency of sound waves. It's really quite high, so trying to measure the period of a sound wave, even just as I'm talking now, the frequency of my voice would be somewhere in the hundreds of hertz, so 200 to 400 sort of range, and so that means that the period is very, very short. So instead of using period, we're going to use frequency, and we know that f is equal to 1 over t. You can see that we've already got that divide by t here, so we can then just substitute in, instead of writing 1 over t, we can write that equation as v is equal to f lambda. So frequency multiplied by the wavelength. That is the wave equation, so fairly easy one to calculate. So in this case, v is the wave speed, and that will be in meters per second. F is the frequency in hertz, and again, just a reminder, frequency in hertz really means that it's number of cycles per second, and lambda is the wavelength in meters. Now, if we look at a particular medium, so let's say we're looking at air, and for a given medium, v will be constant. So the wave speed is constant. Now we can vary that speed, so in air, for example, we can heat the air, and that'll mean that the speed increases. But if we consider it at a set temperature and we sort of keep everything the same, then the speed's going to be constant. So that means if the frequency increases, the wavelength will decrease. And so basically we're then looking at this situation, if we rearrange that equation, we're really saying f is equal to v over lambda, and if we sort of separate that out even more to make it even clearer, we've got v being a constant multiplied by 1 on lambda. So here's our one variable, here's the other variable we're dealing with a constant in between them. So what we can say from that then is that f is inversely proportional to the wavelength. So that means that if we change one, if we increase one, the other will decrease. Sorry, inverse proportion. An example of that, as I mentioned, is sound. If we increase the frequency of sound, that means that the sound waves are going to have a shorter wavelength, because they'll still be moving at the same speed through the medium. There are other proportional relationships we can look at here, but we'll leave that for later, because there's one in particular that will tie into the concept of refraction that will make it a little bit easier to talk about in that video.